In section 2.4, we're going to learn two more differentiation rules. They help us to differentiate things that are products of two variable things, so stuff with x times stuff with x, or quotients of two variable things, stuff with x divided by stuff with x. So far in section 2.2, we had 4 differentiation rules, but none of them really address functions that look like this. So again, f of x times g of x, product, and don't let the f of and the g of stuff like really make this look any fancier than what it is. What it's saying is that if you have stuff with x times stuff with x, right, like variable quantities. Same thing with the quotient rule. Quotient of stuff with x divided by some other stuff with x. So that's all this is saying. Okay, so the product rule tells us how to differentiate something like a product of two variable expressions. So I'm going to use u and v for the product rule, and there's going to be a lot of different letters going on for different things. Hopefully, the more that you practice them, the more you get used to them, the easier it will be. So for the product rule, it says that if u and v both represent functions of x, so they are both like variable things with x in there, then if you want to differentiate the product of u times v, so one way we can write that as u times v in parentheses prime, or the derivative of that. Okay, it is not as easy, unfortunately, as just differentiating the first thing, the u, and differentiating the second thing, the v, and then multiplying them together. It just doesn't work that way. It does work that way if the operation we have is plus or minus, or if the first part here is a number, we have the constant multiple rule, which is different. When we have a product of two variable things, we have to follow this rule. So it says you take the first one, the u, and multiply it by the derivative of the second thing, the v. So this is the first times the derivative of the second, and then plus a second half of this is the opposite. You take the second and multiply by the derivative of the first. So it'll be v times u prime. Another way to notate this, if you like different, we have a couple different ways of notating derivatives. So another way that you could notate this is d dx, which means the derivative of what comes next in the braces instead of a prime. Okay, we can take the first, the u, multiply it by the derivative of v, and that would be dv dx. Okay, instead of like dy dx, we would use dv dx if we're talking about the derivative of v. Then we'll add v times the derivative of u. And in this notation, that would be du dx, would be the derivative of u. Okay, so some notes about this rule. The first note is what I said a little bit earlier. This means that if you are going to take the derivative of a product, u times v prime, it is not just the product of the individual derivatives. There are 0 cases where this is true. Okay, so it would be nice. Unfortunately, this is not how it works. The second note is that this is only needed when u and v are variable quantities, meaning that they have a variable in them, like x or what t, I don't know, whatever it is, as opposed to constants. So if one of them is a number, we have the constant multiple rule from section 2.2, which says that that number can just multiply through when you're taking the derivative instead of, you don't need to use the product rule in that case. So this is only when both u and v have variables in them. The third thing to note is that sometimes, even if you have a product, algebra first is easier than using this rule. For example, if you have a function that looks like this, f of x equals x times the square root of x, it is true that this is a product. We've got x, we could think of that as the u. We've got square root of x, we could think of that as the v. They both have variables in them, but it would be really like overkill to use a product rule on this, because we can use algebra to just simplify this into a single x to a single power. So I would suggest in this case to rewrite this Okay, we have x to the first here. Here we have radical x, which is x to the 1/2. So when we multiply the same base together, we add their powers. So this would be x to the 1 plus 1/2, or x to the 3/2. So I'd rewrite as x to the 3/2 and then use the simple power rule. So in general, if you can use algebra to rewrite something and use our simple rules instead of the product rule, or as we'll see, the quotient rule, you should probably do that. It will be easier and save you some time. So let's look at an example. Our first example is going to be f of x equals 2x minus 1 times 1 minus 3x squared. And just to kind of show you that this, it does work by way of one example, we'll find the derivative of this function without the product rule, and then also with the product rule. So in a lot of cases, you have an option to, again, use algebra first to eliminate a product if that is easier for you. So in this case, we would need to FOIL out to get rid of the product if we were trying to avoid or not use the product rule. Okay, so if we were going to FOIL out this function, or double distribute, or just multiply it out, expand it, let's see, we would get 2x. So just distributing the 2x here, we get 2x times 1 minus 2x times 3x squared. So that'll be 2x minus 6x to the third. Then we'll distribute the negative 1 to the 1 and also to the negative 3x squared. So that'll give us minus 1 and then plus 3x squared. I don't see anything with like terms that we could combine together. However, we might want to rewrite this as with decreasing powers of x. Not wrong to not do this, but sometimes it's just better to have some organization like this with the cubes and the second, then the first, and then the constant. Okay, now we know how to differentiate something that looks like this because we have, done in section 2.2, we have all the tools to differentiate a polynomial. So if we're going to now differentiate, which is the verb for finding the derivative, then we'll have f prime of x. The negative 6 in front of the x cubed is a constant multiple. So we do have a product here with the negative 6 times x cubed. However, they are both not variable things, right? The negative 6 is a constant. So here we're just using the constant multiple rule, negative 6 times 3x squared. Then we'll add the derivative of 3x squared. So again, that 3 right here is, we have a product here, but the 3 is a constant multiple. So the 3 is going to stay, and multiply by the derivative of x squared, which is 2x. Then we'll add the derivative of 2x. So 2 is a constant multiple. So that will multiply by the derivative of x to the first, which is 1. And then we subtract the derivative of 1, which is 0. Now simplifying this, we'll just multiply out negative 6 times 3. We'll multiply 3 times 2, and then 2 times 1. And so here is our derivative of that function using our old methods. So when we do this now with the product rule, we have to get the same thing. That is, of course, always true in mathematics. If you do a problem more than one way, it still has to get you to the same answer. So in this case, let's see what we have if we are using the product rule. Now, either way of approaching this problem is totally 100% correct. It would just be kind of what is easiest for you. However, later on, we will encounter functions that can't have the product removed, and so we'll see that it's necessary in some cases. So here we have a function. If we're going to use the product rule, here's what our u might be, and here's what our v might be. Okay, so if you want to, you can set up this little kind of schematic thing over here. If we write down what u and v are, then next to it, or even below it, if you want to do it the other way. Actually, I think I do it the other way most of the time. So let's see. So there's u and there's v. Then underneath, well, if we look back at our formula here, we need the derivatives of each u and v separately, and then we'll put them into the formula. So the derivative of u prime, the derivative of 2x will be 2 times the derivative of x, which is 1, minus the derivative of 1, which is 0, and so u prime is 2. V prime, the derivative of 1 is 0. We've got minus 3 times the derivative of x squared. That's minus times 2x. And so v prime is negative 6x. Now, if you want to use the formula, like that is fine. Go ahead and do that. If you set it up in this way, then if you make an x here, things that are connected together across the lines are the things that get multiplied. So if we're going to differentiate this, right, just to show you, we have u times v prime, and then plus v times u prime. So the u times the v prime is what's connected by these lines here. So you can just kind of multiply 2x minus 1 times negative 6x. So let's see, we've got 2x minus 1, that's u, times negative 6x, that's v prime. Okay, then we'll add v, which is 1 minus 3x squared. So we leave the second one alone. And then we multiply by the derivative of the first, u prime. So that's right here, that's 2. Now we can simplify this. So, we want to expand out, maybe get rid of the parentheses and combine any like terms if there are any. So if we distribute the negative 6x, we'll have negative 12x squared plus 6x. Then we'll distribute the 2, so it'll be plus 2 minus 6x squared. And if we combine the x squared terms, we've got negative 18x squared plus 6x plus 2. And of course, that is the same as in part A. Okay, so let's look at a second example. Now, I encourage you to pause this video and see if you can work through finding the derivative of this using the product rule on your own. So we could FOIL this out like we just did in the previous example, but just for sake of practicing the product rule, I would really recommend that you use the product rule here. So, here we'll call this one U, and here we'll call this V. So let's see, I'm just going to keep track of it over here. So U will be 4 over x squared plus 5. Now I know that we're going to want to differentiate this, so it'll probably be good if we rewrite 4 over x squared as 4x to the negative 2. Or we always want to get rid of fractions like that when we can. Then V is 1 minus 2x cubed. Nothing to do there to simplify. Okay, so U prime, the derivative of U. The 4 is a constant multiple. X to the negative 2, we bring the negative 2 down and multiply. We subtract 1 from the power, we'll get negative 3. Then we add the derivative of 5, which is 0. And we can sort of simplify this a little bit. We've got 4 times negative 2, which is negative 8, x to the negative 3. Now we do want to kind of convert this back into a fraction without a negative power. We can just wait till the very end to do that, where we'll simplify everything together. All right, V prime, the derivative of 1 is 0. We'll subtract the derivative of 2x squared. That's 2 times the derivative of x, oops, I said 2x cubed, right? So we'll multiply 2 times the derivative of x cubed, which is 3x squared. Okay, so that comes out to be negative 6x squared. So now when we're finding the derivative of the whole thing, so y prime, okay, we just kind of found our pieces here. So now we're going to start to differentiate the entire function. All that is putting into the product rule. Okay, so we take the first times the derivative of the second. So that's u times v prime plus the second times the derivative of the first. So that's v times u prime. Okay, so if we put this into our formula, we'll get u, I'll also write it out here, u times v prime plus v times u prime. So we leave the first thing alone and multiply it by the derivative of the second. That's the u times v prime. Okay, so that'll be 4x to the negative 2 plus 5 times the derivative of the second part times v prime. So that's negative 6x squared. Then we'll add the second v on its own without being differentiated times the derivative of the first, the derivative of u prime. So that's negative 8x to the negative 3. Now at this point, we're just going to be working on simplifying. So it looks like just kind of distributing out, getting rid of those parentheses there. So that's really, we're done with the calculus. Now we're just simplifying. Okay, so we'll distribute the negative 6. So that'll give us negative 24. X to the negative 2 times x to the positive 2. Those exponents will add up to 0, so we'll just get x to the first, x to the 0, which is 1. Then we will distribute the negative 6 into the 5. That's negative 30x to the negative 2. Whoops, to the positive 2. All right, then we'll distribute the negative 8x cubed here into here and here. When we multiply it by the 1, we'll get minus 8x to the negative 3. And when we multiply it into the negative 2x cubed, we'll get positive 16x to the 0, which is 1. Okay, now I think we can combine some like terms together. We've got negative 24 plus 16. So that is negative 8 minus 30x squared. Then we want to rewrite this negative exponent here as a fraction. So the negative 8 is multiplied by the x to the negative 3. So only the negative 8 gets divided by x to the positive 3. Okay, so the x cubed only goes underneath the 8 and nothing else. Only that little part there is a fraction. So there we go. Here's the derivative. Here's y prime. Okay, example number 3 is to find where this function f of x equals 1 over 10 times x squared minus 1 times 7 minus x squared has any horizontal tangent lines. So we have to remember what a horizontal tangent line is. And well, those go like this, right? They are horizontal. They go straight across from, they're flat, straight across from left to right. So they have a slope of 0. Horizontal lines have a slope of 0, but we're not talking about just any line here. We want to find the slope of the tangent line where that is equal to 0. And so this is when the derivative equals 0. Because the derivative tells us the slope of the tangent line. Okay, so we want to find the where, so this is x. We want to find the x values where the derivative is equal to 0. So let us find the derivative. I mean, that's an important piece to all this. So our function here if we write it down to just keep track of what we've got for u and v, it looks like we kind of have 3 things here that are being multiplied. But the one thing that we have in the front, this 1 over 10, that's actually a constant multiple. So this can just multiply by the derivative of what we get by using the product rule. So like when we're finding the derivative of this, okay, this constant multiple will stay and multiply by whatever we get for the derivative of what comes after right here. And this product here, again, we could distribute it out just for the sake of practicing the product rule. Let's use it this time. So, you know, when we find the derivative of this function here, that will go in here, and the 1 over 10 can just multiply through. So let's see, we've got, can call this u, and we can call this v. So u prime then will be the derivative of x squared minus 1. So that's 2x minus 0 or just 2x. Okay, v prime, the derivative of 7 minus x squared, that'll be 0 minus 2x to the first, or just negative 2x to the first. Okay, so I'm putting this together into the product rule formula. We have u times v prime plus v times u prime. So we can make that x there, and whatever is connected to another thing, those things get multiplied together. So we'll get x squared minus 1 times negative 2x. Okay, so where is that coming from? This is the u times v prime. Okay, then we add v times u prime. Okay, so that'll be 7 minus x squared, the second, times the derivative of the first. So that's times 2x. So again, that's v times u prime. And it looks like that is our result of using the product rule. Now at this point, we want to just simplify. So we're kind of done with the calculus. So we just want to simplify here. A lot of calculus is just algebra. Let's distribute the negative 2x into the parentheses. So that will give us negative 2x cubed plus 2x. Then let's distribute this 2x into this set of parentheses. So that'll give us plus 14x minus 2x cubed. Okay, let's further simplify this because we've got some like terms here. The x cubes can combine together. That gives us negative 4x cubed. And then we've got x to the firsts that we can combine together. That gives us 16x to the first. So there's f prime. There is our derivative. that would be the end if that's what we wanted to find, but we want to actually use this now to find where the tangent lines are horizontal. So I want to find where f prime of x is equal to 0. So in other words, set it equal to 0 and solve for x. So we'll say, okay, 0 equals 1 over 10 times negative 4x cubed plus 16x. Now when we're solving for something set equal to 0 and there's an x to different powers in more than one spot, the best thing that we can always do is factor. So on the right-hand side, we've got that 1 over 10 that's already factored out, so let's leave it. We could factor out a negative 4x, that's the GCF. So what we have left when we take that out, looks like we'll have positive x squared minus 4. And x squared minus 4 is a difference of 2 squares. And so I would say we can go a little bit further by factoring that difference of 2 squares into x plus 2 times x minus 2. And so what that tells us now, we have a product of, let's see how many things, 1, 2, 3, 4 things set equaling 0. That means that at least one of these things has to be 0 in order for that to happen. So the 1 over 10 is never 0, so that won't give us any results or anything, nothing useful. The negative 4x, that will be 0 when x equals 0. The x plus 2 will be 0 when x equals negative 2. And the x minus 2 will be 0 when x equals positive 2. And so here are the 3 places where the tangent line is horizontal. Now, if you were to graph this on your calculator, which I encourage you to do, or if you don't have one, you can use something online. The graph of the original function, the one that we started with, it looks something like this. It looks something like that. So this is, again, the original function, the f of x, which is 1 over 10, x squared minus 1, times 7 minus x squared. That guy, the original one we started with. That's the graph of this. So you can see, hopefully you can point out from the graph, like what we found. So here is x equals 0, horizontal tangent line. All right, we've got this low point here. So this is x equals 0, that's what we found there. And then we have this symmetry at negative 2, that's over here. We have another horizontal tangent line. And then at positive 2 over here, we have a third horizontal tangent line. And there's nowhere else, right? We didn't miss any, there's just these 3. So I will actually share with you an app called Desmos. It's not only an app for your iPad or iPhone or whatever kind of mobile device you're using, it's also a website. And it's pretty neat. You can just type in what you are working with. So if we wanted to graph our function here, which was 1 over 10, then we had x squared minus 1. Then we had 7 minus x squared. And you can see in this graph over here, and it's kind of neat, easy to just move around. You can even kind of zoom in. Right, this was the kind of shape that I was sharing with you before. So if you don't want to pull out your calculator sometimes, please make use of this website. It's really neat. If you want to graph even another function, you can graph several on the same set of axes. And I hope you like it. A lot of people tend to prefer it to a calculator. So in the next video, we will learn about the quotient rule, which is our last rule for a while. And I'll see you then.